I'm John Linville, and so I've done this talk before at the assembly. So if you were there, I want to see a couple of faces that may have been, you might be a little familiar. Hopefully that means that I'll have been practiced and professional and polished and all that sort of thing. But it also means that I wrote the original presentation some time ago, and therefore if I trip up a little bit or seem lost, do bear with me. Okay. So let's see, introduction. Who am I? So I'm John Linville. Hopefully most of you know me, if nothing else by voice or by appearing on Facebook or mailing list or something like that. So if you don't know me, then be sure to come by and introduce yourself before you leave the talk. Let's see. So who am I? Could this be me? I don't know if any of you remember this little joke somebody put up where they were giving everyone little personalities or memes. I was the master. Or of course, this is my favorite one, the dartboard. It still gets a little play, a little fun play in the community. I like to think more like this one. So I did Farfall. That's a CoCo game. It's just I'm just a hobbyist and I like to play with this stuff. And if I can help you learn how to do more stuff that you want to do, then maybe between us both make the world a better place. All right, but really, who am I? So I am a serious computing professional. I was initially attracted to the CoCo for serious programming, retro computing. That's back when I was 20 something and had a little chip on my shoulder about why you still playing with these stupid kid computers and all that sort of stuff. But nowadays I've become more interested in writing games and or what I call art projects. Things that just use the CoCo as an object of fun or as something that helps do something fun or silly. So I also am a founder, maybe the founder of the CoCo podcast. If you don't know about the CoCo podcast, I hope your seat is comfortable. You can stay with the next presentation. Let's see, so what is this dairy CoCo? So dairy CoCo is an old phrase that basically means, the CoCo part's new of course, but the dairy part, they used to write books about, all about frogs or all about the world or whatever. It'd be like Dairy Mundi, all about the world, right? So this is a dairy CoCo, all about the CoCo. So really, at least about the base CoCo and CoCo 2 platforms. And it is from a programming perspective, mostly. And okay, that's a leftover line. Testing the waters for a bigger project. Don't worry about that. So the CoCo has always been a great platform for programming in BASIC, right? Anyone disagree?
Nobody disagrees with
that. The cover BASIC hides a lot of the hardware details, and that's why it's there as posted, right? So the problem is, so you get new programmers, and generally if they stick to BASIC, that's fine, but if they become assembly language programmers, one of the things that you hear is kind of okay, I learned how to do loads and stores and adds and whatever. Now what? And there's no print command in assembly language, right? There's you kind of have to figure out how things work and what can you do with the machine. You have to know that and work through it. And so the idea here is to give kind of an overview, a walkthrough, kind of what are the basic capabilities of the machine at a lower level. So if you're wanting to expand yourself in assembly language or C or some other programming language, you're not stuck at the what can I make the machine do level. At least you have some. You may have to be stuck in figuring out how to make it do it, but at least you have some idea of what it could be doing. So let's look at the architecture. So of course it's based on the 6809 CPU. Hopefully we all know that. So a common chart taken from a data sheet shows the two 8-bit accumulators that can be combined as a 16-bit accumulator. Register A, B, and D, of course. The two 16-bit index registers, the two stack pointers, one system stack, one user stack, 16-bit program counter, and then the 8-bit direct page, and the condition code, so those are kind of the special functions. So you normally don't have to deal with, even in assembly language, you normally don't have to deal with them, except at a level of using certain instructions or whatever. But so anyway, start with the 6809. That's the core of the machine. A whole lot of programming the machine though is going to be involved with programming the 6847, which is a video display generator. So that's what provides the video output, 6847. It's clocked at the chroma burst rate, which is 3.5795545 megahertz for NTSC. And the clock comes in from the SAM chip. Data is addressed via the SAM chip. The least significant bit of the address bus and the async are used for synchronization between the 6847 and the SAM. So the point here, sorry, this is one of the places where I skipped, I forgot the point. The point here is that in the CoCo, the address lines that come out from the 6847, they're designed to drive memory for accessing video or whatever, but they're actually not connected. They're not used in the CoCo. The addressing actually comes from the SAM chip, not from the video chip. This has at least one special benefit. I think it'll be on this slide or the next one. But anyway, I'll get back to that. There are mode control lines on the 6847 for alpha or semi-graphics or for inverted text. These are control lines that are actually controlled literally by hardware signals, whereas you might think a video mode would be set in software. In this case, these video modes are set actually in hardware signals. And they are used, these are controlled via the data bus, which is why semi-graphics modes are controlled by having a high bit set in the data of what you're displaying. And also this, the inverse video is controlled by one of the data lines. And so this actually was recommended in the data sheet for the SAM 6847. Let's see. There are some other mode control lines for, again, it's not controlled with a software register, it's controlled with actual physical inputs to the BDG for your video modes. They're connected to the 5 most significant bits of port, PIA port, the PIA port at hexadecimal FF22. Okay, so here's an example of what the text mode and semi-graphics 4 mode of the CoCo of the CK47 looks like. Should look familiar to any of us who ever used the machine. Here's the color graphics, the 6 mode, so higher res. Just an example. So the CSS pin, which is one of the mode select pins, set to 0. And when it's set to 1, you get the opposite color step. So again, that's the physical signals going into the 6847, determining the video modes, which is a little bit different from a lot of other systems. Anyway, here we are. So this is from Farfall. This is in what we call SG12 mode. And so this is one of the special modes that I mentioned earlier, that the address pins on the 6847 are essentially disconnected. But that has an interesting benefit in that you can essentially, sort of lie to the chip, telling the other, the PIA pins that tell it what mode it's in. And then you can tell the SAM some different information. And so because it's the BDG is relying on the SAM to fetch the memory for video, the SAM can go and fetch memory in a different fashion than what the video chip would have done, which enables essentially a different style of video mode. And so in this case, the main benefit here is that you get more blinds. So what would be, normally you'd have blocks, 2 by 2 blocks, with each block being 6 lines high for a total of 12 lines for a character. In this case, you split it up a little differently, and so you've got these lines are only um, 6. No, I can't remember exactly now. Sorry. Anyway, there are fewer lines until you get a higher resolution mode effectively. And even though there's still kind of a little strangely how you allocate colors, it's still, it gives you a prettier mode or a higher resolution mode. Let's see, so moving on now to the SAM. SAM is a synchronous address multiplexer, and it kind of glues the rest of the system together. It does the DRAM control, address decoding, so it actually has signals that control the various devices on the system bus. It also provides the clock control back to the CPU, which enables it to have a couple of different clocking modes, so different speeds effectively. You get a system clock divided by 4 or a system clock divided by 2, so you get a couple of different speeds. So it does integrate with the VDG to share the DRAM between the CPU and the VDG, and it's sort of a system detail, but it's just there. And as I was saying, the VDG and the SAM combination enables extra video modes, which includes SG8, SG12, SG24. So basically, you take those SG4 blocks. Like I said, there's 6 lines in each of those, 2 by 2, and then each of those other modes is basically you go from 6 to one has 3 lines, one has 2 lines, one has 1 line, and so obviously the fewer lines in the blocks, the higher resolution you get. So anyway, neat feature. Moving on, we have 2 peripheral interface adapter chips as part of the architecture. Each of these has 2 8-bit bidirectional I/O ports. They both have 2 1-bit interrupt inputs, so you can actually trigger an interrupt from a pin going into the PIA. They have 2 1-bit peripheral control signals. And so they can, you can control things. You can connect things to the PIA and control them. And in the CoCo, they're connected in a very special way, which again we'll get to in a little bit. The PIAs are used with various hardware constructs to implement all the other peripherals that are part of the CoCo. So this is where you get to things in the CoCo that are kind of built from other things. So one of the most important things we have is 6-bit DAC. So we have 6 resistors in an R to 2R configuration. They're connected to the 6 most significant bits of hex FF20 or FF20. You get a V out range from 1/4 to 4 3/4 volts. It's primarily used for generating audio output, which also includes cassette output, which of course is audio as well. Okay, so one of the maybe lesser known or lesser appreciated bits of the CoCo architecture is the MC 14529V dual 4-channel analog multiplexer. So you've got 2 channels. So one channel selects the audio output that goes to the RF modulator, which happens to be enabled by bit 0 of FF22. And then the other side selects which joystick axis is the input to the comparator, which is, again, we'll get to in a little bit. The kind of quirky thing is that both sides of the mux are controlled by the same selector inputs, so they switch at the same time. And since one of those is related to audio and one's related to joysticks, if you're checking the joysticks, you're messing with the audio, so you have to handle that carefully. There are techniques to avoid that or to mitigate that, but it's basically impossible to escape. So some care must be taken to minimize or avoid clicking and popping sounds when using the joysticks and playing audio. Okay, so we have a comparator. Actually, I have a couple of these. So in the simplest form, a comparator is essentially an op amp wired in a certain way. And let's see, so what was I writing? Comparator enables software to use the DAC to do ADC, so digital audio converter to do digital to analog converter to do analog to digital conversion. So, so the output of the DAC is used as a reference to this comparator circuit, and the MUX output connects to the joystick axis to the other input. And so since this acts as a comparator, the comparator output can then indicate which of the two signals is bigger or larger voltage. And that's indicated on bit 7 at FF00. And then you use software to drive the ADC through a successive approximation, which could be a linear, try each value, or it could be a logarithmic approach, is what I prefer. Some people don't like the logarithmic approach because they're convinced that it doesn't settle fast enough. I'm not sure if I've seen any actual evidence of that. If anyone has any proof of that, I'd like to hear it. Anyway. Okay, so the zero crossing detector. So we have another comparator. It's connected between the cassette audio input and a fixed 1 volt. Go ahead.
So I'm ignorant about some of the CoCo stuff. So you're driving, so you're in a game, and you're creating audio.
Okay.
And now you're creating the joystick.
Mm-hmm.
So you flip back, you do a successor approximation on the joystick, and you
yeah. Yeah, no,
it's crazy, right?
It's an issue to be dealt with, and so you need to figure out, some way to silence your audio output for some period, or otherwise mitigate it by setting the DAC value before you do the switching for the joystick.
When you flip over to the joystick, what happens to the audio side? Does it just float, or does it like?
It just floats. So it's a difficult problem to deal with. Basically, I don't have a good solution there. The best solution I have is to allocate to select a joystick input that is unrelated to your audio outputs, and so that they don't screw with each other as much, or sometimes at all, depending on.
So you synchronize your
You
joystick.
skip it.
When you minimize your noise.
Right. So
that zero crossing detection, how you ever did the audio spectrum analyzer?
I'll mention that. Yeah. So so basically the zero crossing detector is another comparator. So you can use zero crossings over time as an indicator of frequency. And again, that showed up as 0 at FF20. So you can use this to discriminate different tones, but there's maybe other applications, including the audio spectrum analyzer. You could do a radio facsimile. Maybe you could do a software modem. Might have to be a slow one, but you probably could do it. Morse code, possible. Anyway, that's I'm lost now. Yeah. Okay. So just some possible applications, just suggestions. All right. So the cartridge port, mostly a hardware thing, but you need some awareness of it to be able to make use of it. Let's see. So the signals that are on the cartridge port, there's a line halt. That's a signal. Well, I'm not going to read them all to you, but there is a halt line which will allow you to stop the CPU. There's an NMI, so non-maskable interrupt line, so that you can demand attention for your hardware device. There's a reset line if you want to, if your hardware device needs to be able to reset to CoCo. I don't know if that's a good idea to do under software, but maybe it is. It's up to you. So E and Q are the two clock signals, the quadrature clocks. CART, I think it's a poorly named signal. CART is actually an interrupt line. It gets tied back into the fast interrupt request line on the 6809. And it has to be selected. Anyway, so CTS is one of the kind of pre-set up address decoding lines on the CoCo. So that's what's used for selecting the cartridge ROM. So yeah, okay, there is a SND or sound, so you can actually have a sound source on the cartridge, and that's what's used, for example, on the Game Master cartridge hardware, or also used on the I can't think having a brain fart right now, the Orchestra 90 or the Sound Speech Pack. So SCS, it's another cartridge select line, but this one that's in the I/O space. So really it's designed for the floppy controller. It can be used by anything, but that's sort of what it's there for. And then SlimB, the most misunderstood line on the cartridge port. SlimB basically turns off all the existing decoding that's on the motherboard. This may have been a questionable use, but there are devices that need to use it, and there are some rules about how the multi-tag interface uses it. And so, if you're designing hardware for the CoCo and you want to build a cartridge port, especially something beyond that's not just a ROM pack or whatever, then you may want to do some research and make sure you understand the signal. All right, so there's a keyboard provided by a switch matrix connected to the PIA ports. You got 8 columns attached to PIA port at FFO2, and they're set up as outputs. You have 7 rows attached to the PIA port at FF00, and they're configured as inputs. So you scan these by bringing one column low at a time. So by outputting FE, FD, FB, those kind of, those each have their walking 0 bits in there. And then you read back on the other side. So anything that's reading low indicates that the key's been pressed, and then you have to map that to the matrix to figure out which key you're dealing with. Obviously, or maybe it's not obvious, but the Dragon computer, it's got a similar matrix, a similar method for scanning. The matrix itself is slightly different, although oddly, well, maybe not oddly, but I guess it's their rows. They have the same 7 rows, but they're in a different order. So like I don't remember what the rows are, but say there's a row that has letters A, F, Q, and R, or whatever. There's an exact same combination on the Dragon matrix, but it's just on a different row. Is that useful? Might be useful if you're trying to write code that'll run on both the CoCo and the Dragon that accesses the keyboard. So that way you can maybe you can use the same code just by changing a bit mask somewhere when you're testing things. I don't know. Your mileage may vary. Let me know if you have a problem. Okay, joysticks. So this is a picture taken from the manual. What am I trying to say? The technical manual. There you go. And so the joystick is pretty simple. You see, you've got 200K potentiometers, and you got one switch that connects to ground, 5 pins on the input. It's not that hard. But there you go. That's how they look. The the CoCo 3, sorry. The CoCo 3 supports 2 joystick buttons. So the schematic is pretty much the same, except that there's 2 switches that connect to ground. The second one connects to pin 6 of the DIN, which is right in the middle of the pins shown here. So, all right. So the cassette interface, which is, like I said, it's kind of a construct. But anyway, the audio interface is designed around 80s era consumer tape decks. I'm sure we all remember those. Everybody had one back in the day. So you get output from the 6-foot DAC. So you get input through the zero crossing detector. There's also a PIA controlled relay as a wired remote. And so this was a mechanism that those old tape decks often had that let you turn it on and off, basically by connecting two wires together. And this is why the CoCo could have you could press play and it didn't move until you just actually did a C load or whatever, which also enabled you to have applications that would run the tape separately, under software control, whatever. Yeah, then that's the relay you hear click, right? And so is this useful? I don't know. What application are you going to write? It's up to you to figure out how to use these things. I'm just walking you through it. So, okay, of course, we've all heard of the bit banger, the RS-232. It's a software-driven serial board using PIA pins for the signaling. You have one output pin for transmit, two input pins, one for receive, and one ostensibly for carrier detect. Not really used that way. Let's see, the IO pin voltages are then level shifted to match RS-232. So bit banged IO is prone to missing incoming characters, so you're probably going to have to stick to a 300 BPS or so max. There are some ways around this. For example, the drive wire it kind of gets away from that, is able to go faster, but it's because the drive wire protocol is essentially synchronous, and so it knows when the data is supposed to come, and so it doesn't miss it, it's waiting for it. All right, so there's an op amp used for transmit level shifting on the CoCo 1, and that is slower than the equivalent circuit in the salt chip that's on the CoCo 2 and 3. Why did I say that? It is possible to do an upgrade of the op amp and be able to use that to go a little faster if that's important. Just so you know.
So the limit is the slew to the op amp?
Exactly. I think if you switch out a TLO82, it's sufficient to be able to get it up to a 115.2 in a bit per second.
So it's not the clock rate process.
That's right. Yeah. All right. So what else can we do? We can do so PCM or pulse code modulated audio. This is through the DAC. Just so the example here showing a sine wave, and you see the blue dots to represent the various samples. So if you want to reproduce a sine wave, you need to know what the sine wave looks like, and shift out the samples yourself to the DAC as appropriately timed. So it looks something like the picture there. There is a 1-bit beeper audio output. So it's a 1 digital IO pin that's mixed into the audio output. This is bit 1 at FF22. It's not routed through the 4-way mux. And so that's, that can be useful or it's something to worry about. It kind of depends on what you're doing. So you can use this to do CPU-driven 1-bit audio. It can be pulse code modulation, like we showed previously. You can do pulse width modulation. You can even do pulse density modulation. Who knows the difference? Yeah, I'm not going to explain it either, but there are variations on the theme. But if you can do it, it's more about what the software does. All right, so interrupt sources. Hardware interrupts are a useful means of synchronization with real-world events. So the CoCo provides several interrupt facilities that might be useful. So you have an NMI or non-maskable interrupt input from the cartridge port. So that's, depending on your application, that may or may not be truly useful, but if you need a non-maskable interrupt, that's where you get it. There's the IRQ lines. This is traditional slower interrupt source for the 6809. Um, this is actually tied into the hardware on board, particularly the BDG. Um, and it's kind of already used, but if you need that to make use of them, you should be aware of it. They're tied into the V-Sync input from the BDG and the H-Sync input from the BDG. H-Sync actually is basically too fast to be useful in most cases. Basically, by the time you've gone through the exercise of executing the interrupt, the IRQ, you don't have any time left to do anything. Now, Simon Jonason observed that you could essentially just ignore one of your IRQs or eat one basically. So as you get two IRQ periods used as one, and you can actually do some useful work in that case. So just know your machine, I guess.
The Animalite, what's that service?
Nothing, just what's out on the whatever's out on the port that wants to generate it.
What is it? What does the Animalite jump to whenever it's requested? Service.
There's a vector defined for the 6809. That's
So just whatever's in that vector, it doesn't have a specific thing.
Right. Yeah. I mean, it shouldn't happen. It's basically what it amounts to. If you build the hardware that'll make it happen, well, then that's on you.
But that is, I just want to make sure it wasn't dedicated to a specific.
Yeah, there's nothing out there right now. Okay, so there's the fast IRQ line. This is on the 6809. This is the special version of IRQ that doesn't stack the registers. So it's a little faster. It's only available through the cartridge port, and there's no cartridges normally that generate it. But if you want to build some hardware that generates an interrupt, you can go through the cartridge port, and you can have something that goes a little faster if you want to. Again, it's on you. If you break it, you get to keep both halves. Now, again, in some cases it does. This can be connected to the CD or carry detect line on the RS-232 port, and then I can't remember if that's only on the CoCo 3 or not. So there has been work in the past that has tried to make use of that to go faster on the serial port back in the days when people were using modems and trying to go fast on serial ports. I'm not sure any of them actually worked out very well, but if you need to use it, you have to figure it out. But that's there. This is the tool. All right, so let's talk about some software scenarios. Okay, so this is the data sheet description of selecting modes on 6847 and the combination of that with the SAM. And it's clear, right? I don't need to cover that. Okay. There's a lot to be had there. The point being is that the actual mode that you get is a combination of the setting between the 6883 or SAM and the 6847. Good. Assembly code, let's see, what are we doing here? So, yes, configuration of the SAM is done in kind of a quirky way where you actually do you access certain addresses and it sets bits inside the configuration memory of the SAM. And so here we go, this first few, there's a clear and another clear and another clear, and those are clearing and then setting a bit in the SAM, and then it loads up hex value CA and stores that out to the PIA. So that's setting those external bits on the BDG for the mode in question. Also, part of the SAM configuration specifies the base address for the video memory, and that's also done with the accesses to certain memory locations. And that's at the bottom of this clear FF, C7, C9, CB, CC, CE, DO, and D2 are set in the video base, in this case to X0E00. So that's an example of setting a video mode of your program.
Video offset.
The what?
It's the same offset.
The FFC stuff? Those are the basic, those are the address registers that the SAM was looking for. Address values that SAM was looking for setting this configuration. Okay, so plotting pixels. Basically, they're memory mapped in the video buffer. So I've got a little picture here demonstrating how the bits look in memory. In this case, we're talking about a 4-color mode, and so you've got a byte, and they have 4 pixels described, 2 bits per pixel, and they're packed in like that. So if you actually want to locate a pixel, it's a fairly simple math problem. Start at the screen base address. You add a multiple of y by the line width, y being the Cartesian coordinate, not the register, but a multiple of y by the line width in bytes, which is determined by the video mode you've set up. You add the x modulo number of pixels per byte, and then you read the existing byte from the pixel byte address, which is what you were determining earlier. And then you modify the relevant bits if you want to just modify, 1 bit inside the byte. So, this is pretty simple stuff, but just walking through it. Of course, then you write the modified byte back. Okay, here's some more assembly sample code. This is reading joysticks. Basically, looking at the comments, of course. The top stanza there is selecting the right and left axis of the left joystick, and then setting up the DAC to test for the value, the X65 value, and then depending on whether it's higher or lower, jumps to different location. You might test for the hex 98 value, also higher or lower, it goes to different locations. So you can kind of see how that is used to do test your joystick value. If it's not clear, feel free to ask me afterwards. All right. Okay, playing music. There's many ways to make music on the CoCo. Again, there's a 1-bit PCM or PWM or PDM. You may need a little help from software trying to figure out what values and what timing you'll need to generate whatever music you want to do. But you can do it that way. Of course, you can use the 6-bit PCM, which is the standard way using the DAC. You can use the cassette playback for making audio. Or, of course, you can have some sort of audio synthesizer on a cartridge. Prime example for me would be the Game Master cartridge. So, let's just review. So, in any of these cases, you would select the audio source with the 4-way mux as necessary. You would enable the audio output at the mux. Again, if it's necessary, depending on exactly what source you're using. You're going to set up any timing sources. So if you're doing a software-based synthesis, you're going to need something that times how long before you transition the wave for the audio for the tone. And you're going to have some number of those running. And then you also need a timing source that's a little more coarse that's going to basically indicate when you actually change the note itself. So if you're synthesizing in software, you have to set up those timing sources. If you're using hardware synthesis, just configuring the hardware. So fine time is needed for tone generation. Of course, time is needed for note changes. All right, or you can then just start the cassette, turn on the synthesizer, or just start synthesizing right there. So playing music, simple. Any questions? Okay, so reaching the conclusion. Hooray! All right, so the CoCo remains a rich and rewarding computing and gaming platform for many to this day. Hopefully, this is the right audience to say that. So with this peek on the inside, what can you make the CoCo do for you or for all of us? So it's my little challenge. So, do you want to have any questions? make you ask questions.
The audio, methods of creating audio, what's the frequency range of sine wave thinking? Do you know off the top of your head?
The sound waves that you can hear, or I don't
Yeah,
know.
did you want whatever, I mean, can it go down to 10 hertz and up to 20 hertz?
Well, I mean, you
It'll
know,
still be a sine wave, or does it, it starts falling apart? Because I mean, you're basically doing this DAC that's not a DAC, it's 6-bit belts, and then then you get time between the rise and fall time.
yeah, well, I mean, so it comes down to a math problem.
Yeah.
Saying, so you've got the 0.89 megahertz normal clock speed for the CPU,
So it's what
and whatever tones you want to generate, and how often you're going to allow yourself to process the
other stuff.
yeah. So it's sort of like I said, it's just a math problem. If you can't process it fast enough for whatever tone you want to generate, obviously it's just not going to work. You also have to factor in, how thin are you slicing the steps on the output. So I mean, you can make smaller steps and
All
it sounds a little
all this
better.
stuff's basically being controlled by your code.
Absolutely.
I mean, it's a single stream, no multi-thread, anything like that, on any line. There's no hardware out there other than DACs and stuff like that. To make sort of the sound control of the process.
Well, there's music programs that kind of multi-slice, if you will, to create multiple frequencies, even though you have to have one output.
Yeah, but I mean, it's a simple matter of programming. Is the term,
Simple
right?
metals.
Another thing too, AC from, I think it was AC from AC's Acres the sine wave cable for generating a cassette output for like writing out the cassette, he modified it, made it shorter, so it would go quicker, and he actually proved that you could improve the heck out of cassette speeds.
Yeah, I saw that video. I remember thinking that I didn't agree with what he was doing, but I don't remember what the disagreement was.
It's probably done the way it was done, so it's more reliable.
I think it's one of those where he fixed the problem he was having, but he didn't really. He wasn't actually addressing the more difficult problem. Well, yeah, it's neat. It's good analysis and good that he got to work in. But I just felt like it. I remember thinking that it was some other ship that was actually the problem. So anyway, and I could be wrong. Anything else?
Has there been other efforts put into hardware to increase the memory size to 128
Like for the CoCo 2 or the CoCo 3 rather? Oh, sure. I mean, there's solutions available for 2 megabytes out on the floor probably.
If you go to the index.
So there are other options available.
And then that's also driven a lot by the code as well. Maybe address that higher.
Well, yeah, I mean, if you're looking for existing programs, the only thing that's going to use more than 512 or 256 or whatever is going to be OS 9.
Yeah.
And, if you're not, I mean, it's not the only thing, but there's not a lot. And especially when you get out to beyond 2 meg or 8 meg or whatever, there's almost nothing. And when you get to higher amounts of memory, managing the memory itself becomes enough of a task that it's not necessarily worthwhile.
Sandwiches and
Well,
up to 512.
well, of course, the SAM is on the CoCo 1 and 2. The Gimme is handling stuff on the CoCo 3.
That's right.
Anything else? Go ahead.
The young to use cassettes to load. But
You're feeling mighty unlucky you are.
You're lucky.
Despite the beginnings of the gray and the sideburns.
I played cassettes in there too. So I'm gonna ask a bunch of questions. But so are you using the frequency modulation to store your 1 and 0s off the cassette? I assume
That's right.
I don't want a 300 baud modem type style.
Exactly.
And is there a standard, adhere to standard, or is it an ad hoc, as you will, type situation? And then the third question is, can you just blast a square wave to make those frequencies, or do you have to use the
Okay, so there were standards, including something called the Kansas City standard, which was supposed to be generic. It's pretty much immediately violated by anybody who actually used it to make it more custom to those particular machines. It's similar to what the CoCo does, not exactly the same. For example, the Kansas City standard, I think, mandates a certain number of cycles for at a given tone frequency, a certain number of cycles before the bid is counted. Whereas on the CoCo, it's the tone that you're using. You do that frequency, you do one cycle, and usually that's good enough. Maybe not, whatever. But yeah, that's what you're dealing with. So right there is a difference, right? And so a lot of machines did some different things, and some of them could stay compatible, some of them maybe didn't do it well. So the MC10, for example, is using essentially the same technique to store to cassette as what the CoCo uses, and the MC10 only has a square wave output. So yeah, it is possible to do it. And sometimes it works better than others. So it just kind of depends. But so yeah, it's possible.
And I'm like, you can do an all RAM mode and modify the sign.
You can mess with that if you want to and change. You can make it a little. I think basically what the AC thing was doing, he actually made it a little flatter, and it would work better for him because I think his equipment was
More modern digital.
to cutting the tops off the waves, basically. Anyway, I haven't watched the video in a while. I remember thinking there was a different solution, but anyway.
I remember he didn't do a test cell, but it was remarkably faster.
Yeah, well, basically, he addressed the problem that his machine was having and made things work better. But I wasn't convinced that the problem that he addressed was a truly generic issue. It's like, this car has a flat tire, so let's pump it up. Not every car needs a higher air pressure in the tire. You know what I'm saying?
Yeah.
Something like that.
And follow up, so then once you get above the analog domain, you're stepping into like digital. Is it kind of like an asynchronous serial port where you have a start bit and stop bit?
On the cassette loader?
Yeah, on the cassette.
Let's see, how does that work? Yeah, no, I don't think there's quite an analog to it. It's like a start bit or whatever. I think it basically just is the wave is started and this and it's finished, and it's just like that. Like I said, the Kansas City standard was a little more robust, and it mandated some number of actual waves for a given a bit. But the CoCo stuff, I'm pretty sure it's one wave for a given bit, and which works mostly. Maybe not quite as robust, but anyway. How are we doing on time? What time are we supposed to?
It's 20 after 2.
What time?
14:19.
What time are we supposed to stop? I guess is the question.
I have no idea.
It says here, 1:30 to 2:30 is
Okay,
human, and 2:30 to 3:30 is the CoCo group.
Okay, so technically we have a few more minutes. If anyone has any more questions, go ahead. Anyone?
One thing I like about the cassette, the only thing I like about cassette, I hated cassette.
You can put a different cassette in this.
Yeah, I mean, back in the day, cassettes were unreliable and slow. But the one thing I really liked about the CoCo, or the cassette on the cassette, was the audio output of the cassette, or the output, was auto modulated and came out the sound of the television. And Disney had come out with these educational programs where, and you could also turn the motor on and off through software, and you could turn the speaker on and off through software. So they would turn the speaker off and load the program, or you would load the program like you loaded any program. When it executed, it would keep the motor off and load data for graphics. Then it would stop the motor, and then the graphics would come up and start the motor, and you'd hear audio, someone a recorded voice, playing through the television.
It's like a foot.
Yeah, it was multimedia before multimedia existed. And it was really cool. I just thought that was like the coolest thing where they could mix data and audio, more data, the speaker would shut off, the motor would kick on, play, it would load more graphical data for the next set or next couple of frames that it was going to display. And it was really well done. And I always thought that was the coolest thing because it did, that kind of media was like 15, 20 years away before CDs became.
So in case that didn't translate to streaming, just having some reminiscing about how you could have cassettes play and come actually under control of the CoCo and then play out through the TV. And if you were clever, or if whoever programming was clever, they could actually make good use of that. You get a combined experience. So, go ahead.
I heard references a couple times to a technique to get high resolution joystick feedback without the hardware device.
Yes.
Are you familiar with how that works? Because
I certainly don't know it well enough to explain it.
or no,
Basically,
who actually
Nick Rennie came up with that idea, I think, or someone, Nick was
I
talking
think it
to
was a combination of Nick and Stockmaster.
Stockmaster, I think, came up with the idea, and then Nick coded it. It's basically the same joystick routine, it's just tighter. You're spending more on the CPU sampling the joystick port.
There's some modeling of the actual interaction, the analog interaction of the potentiometer, so that basically doing some modeling of the actual RC transfer functions, and so that predicting what the in-between values might have been based on, if you sample it 2 different times, there's a difference.
Okay, that's what I was curious. There was like a probability type of thing where I sample it 10 times, and if it's more likely to be closer to this one, closer to that one.
Yeah, I mean, it's a little bit of voodoo, but it seems to work pretty well.
Yeah.
If I remember correctly, the only way that worked is if you had the set recorder sitting on the table upside down.
And you sacrifice the chickens.
Yeah, exactly. Anyway,
Thank you very much.
anyone needs to contact me, pretty available. And of course, feel free to listen to the podcast and come see us in Springfield, Ohio, in the beginning of October. In September.
Can you throw that email address back up for a moment? Thank you.
You have a Red Hat mailbox?
Sure,
Did you do some work for Red Hat?
I work for Red Hat.
Oh, that's great. What do you do for them?
I'm on the kernel team.
Oh, that's awesome.
Yes.
That's exciting.
For Rails specifically, yeah.
That's gotta be great.
Well, it's interesting.
Does your team submit, code?
Sure.
Okay.
Yeah, I mean, it's at different times we submit to different targets. We participate upstream at some point. It depends on like bug fixes or whatever. But typically our job is to take changes from upstream and back working to real kernel architecture. Typically based on all of them.
Has Linus personally cussed you out yet? I've heard that's it's like a hallmark of Linux kernel development, rite of passage. You get cussed out by
more so
Linus.
than it is today, but I'm pretty sure I've got some Linus burns somewhere. Not
So,
really
did you
that
say some Linus burns?
bad. Yeah.
That's funny.
Are you gonna run right into the CoCo cruise, or is there a break, a small break before that?
Just a break would be fine, I guess.
Yeah.